Well, after learning linear regression model in this chapter, we're going to extend and generalize the model structure to be nonlinear. In this case, your f function your y, the explained variable, is related to the predictor via a nonlinear function in f. But we're gonna focus down on this representation that your function f can be described as linear combination of basis functions, right? So these has provided a very big, a wide class of representation in F. And then we're gonna consider one particular representation where the basis function are splines, right? So we talk about regression splines and smoothing splines at the end. So first, let's think about how you want to represent y as a function of x. In the linear regression, we see this linear representation, right? Where y is a linear combination of the predictors. And a lot of times, we also talk about the extension that you can also suppose you have only one predictor, like just one x, but you can also consider a polynomial function in x, right? Which means the second term is beta 1x, the third term is beta 2x squared. All right. So in this example, this is a polynomial function in x which is nonlinear, but it still fits to the framework of linear least square, because this representation can be described as a linear combination where it's linearly parameterized in the regression coefficients. All right. So from that, we can extend this concept where your function f is a linear combination of basis functions, denoted by the function g. Okay. Here, the index I means that this is the response of sample I. All right. You have data of big N samples. The basis functions gk are supposed to be given, supposed to be known with the expression provided by users. For example, of course, when gj, each basis function is just basically linear function in the predictor. Of course, these I'm going to call model one. Model 1 just fall back into the linear regression model. Okay, if Gij, okay, Gij can be a power in xj, second order, third order, or maybe the term that is a product between two predictors, xj and xk. Of course, these will give you polynomial function with the crossing term, interaction term. Okay. Another examples of nonlinear, it can be the log, function log, right? Function log of predictors xj, or the square root function. Okay, so these represent some examples of nonlinear transformation. Or the last example, it can be indicator function. Okay, with the indicator function means indicator function is typically defined with respect to some set, all right, some criterion of x. Okay, so this means that it returns 1 when x belongs to that set, or if x satisfies criterion, and returns 0 otherwise, right? So with this notation, so basically it means that whenever xk is between window interval L and U, the function returns 1 and 0 otherwise. Okay. So So with GJ, with this example of GJ, it would mean that you partition the range of the predictors. Suppose your predictors are between -1 and 10. Suppose this is the range of your explained variable, and you would like to use each basis function with different that define on different intervals of x. For example, this is the first indicator function. All right. So the suppose, and the green, all right, and the last is the red one. Okay. Suppose I put the mark down -1, -1/2, and then this is 2, for example. So this is my G1, this is my G2, this is my G3. With this example, it means that I decompose function y into what? Into a basically piecewise constant, a constant function. But that constant, that piecewise constant is defined, is named as piecewise because it's a constant within some subintervals of x. Okay. So with all these examples, you know that when you represent f as a combination of basis function, the model is nice in the sense that it's linearly parameterized in beta k. All right, as long as the basis functions are given, which means given with this math expression, you can basically solve beta k by using the linear least square approach. This is an example of the wage data set provided from ISLR textbook. All right. So this is the income of population in the group of interest. They would like to explain if the age, all right, like old people, young people, do they have the same amount of income or not? All right. So the blue dots, of course, the gray dots are data set. Here is an example of piecewise constant. So here you define the breakpoint, right? You define the breakpoint, the point where you allow the piecewise constant to switch, okay? And then, which means the breakpoint here are the values of Ci, and it depends on you how many breakpoints you want to use. And then you're gonna fit, right? You're gonna fit. So suppose here is y equals beta 0, beta 1 times indicator function from C1 x and C2, right? And beta 2 times indicator function C2 x and C3, for example. And then you want to estimate this beta k. Okay, and the result turns out to be the green value. Okay. So this is some example. So we would like to make a comment that in this chapter, of course we still want to achieve the ultimate goal, which means we want to develop a good representation f, a flexible one. We of course we refer to the term flexible because we want f to be to explain the data y very well. Okay. And of course, what we have learned so far is that polynomial functions are one of the good choice, but the thing is, one drawback is that it doesn't generalize well when you test on the data set that has different range. For example, if your data, suppose your data, the blue one, you train it in between the range of 1 and 10, right? Suppose the green is the polynomial fit you obtain, okay? But then when you use, of course, when you use in the future, probably the range of your predictor might extend to 1 to 20, okay? So of course, in this interval, it will the behavior of your function polynomial is the one you train from this set. So, and everyone knows that in the polynomial function is actually characterized by the polynomial coefficients. And the polynomial coefficients, if you just tweak a little bit, all right, it's I mean, its behavior can change. So polynomials model may be limited by this observation, by their global nature. Okay, so that's why in this chapter we take the direction to the approach that we want to develop flexible models, but this flexibility comes from the fact that we're gonna chop the interval of x into pieces, okay? And we try to like this curve, right? You kind of see like overall trend, like maybe something like this. So what we do is why don't we kind of consider different intervals of x and try to develop a local polynomial function that best explain y in each interval. And that is the concept of regression splines. Okay, it's local representation. Okay, and then but because you consider different intervals of the ranges in x, and that's how you introduce more flexibility to the model. So regression splines. Okay, regression splines, the definition is basically this. You have predictors x. Okay, you user define knots or the breakpoints. Suppose the breakpoints in this picture is indicated by the vertical line. Okay, and if you have k breakpoint, k knots, all right. In this example, you have C1 and C2. These are two knots. Of course, the region of the predictor will be k plus 1 regions. In this picture, two knots, 3 regions. And what we do is we're gonna fit piecewise polynomial to each x. I use x1 and y1, but what I mean is that all the samples that contain in region 1, all right? It doesn't mean the sample 1, all right? So x2, y2, these mean you collect all data points in the second regions and then fit a piecewise polynomial, right? So this is the piecewise polynomial fit or the regression splines. In this graph, I show you linear, all right, linear polynomial and the fourth order. So mathematically, it basically means you have k knots, right? You have C1, ck. These are breakpoints. How many polynomial will you will be fit, Panat? Panat.
3, right?
Oh, k knots. Suppose in general you have k knots, which means you have k plus 1 regions. So how many polynomial will be fit? Panat.
K plus 1, right?
K plus 1. Okay. So each of the polynomial is actually this is polynomial 1. Sometimes it's called the first piece in terms of how they refer to it in the computer library. Piece 1, piece 2, and dot define on different regions of x. Okay, and suppose a polynomial of degree n. All right, it has the form of course a0 plus a1x plus an x to the n. All right, this is a polynomial of degree n. Trung, polynomial of degree n. How many parameters does it have?
Yes, n plus 1, Ashan.
N plus 1, right? Okay, so if we fit regression splines, all right, so if we fit n degree polynomials with k knots, but k naught has k plus 1 regions, k plus 1 polynomials, each has n plus 1 parameters. So the total number of parameter counts would be n plus 1 times k plus 1. This is the total degree of freedoms of regression splines. Okay, see, you introduce more flexibility, more degree of freedom because of this factor k plus 1 when you chop off the interval of predictors of x. You can increase even more flexibility by introducing higher order term in polynomial. Okay, so there are two ways. It's not a trade-off. There are two ways to increase degree of freedom. Immediate flaw, the first big advantage of this, of how you pose the problem in this way is, of course, if you look at the graph, when I consider region 1, right, the red line is the best polynomial that fit to the data set in the region 1, and the yellow, so on. You can see that the obvious fact is that these piecewise polynomial, they don't joint. I mean, they are not joined together because of what? Because each of them are optimized independently. All right. So when the functions at the boundary or at the knot, when the function value at the knot are not equal by, you know, first and the second polynomial, it means that your overall polynomial or the function, they are not continuous at the breakpoints, and that is the one first obvious flaw. So that's why the next step is, of course, you're going to introduce constraints. And these are continuity constraints in the function value. All right. So P represents the polynomial. So at the breakpoint, suppose at the breakpoint C, the jth polynomial and the j plus 1 polynomial, all right, the function value have to be the same. That is the concept of continuity. Furthermore, you may want the spline. Okay, this is called regression spline. You want spline to be smooth, and the smoothness is quantified by the continuity in the first and the second derivative, and of course higher order derivative. All right. So for example, in the first order derivative, this is what? First order derivative, polynomial j and j plus 1, they must be the same at the breakpoint. Okay. Whenever you impose one constraint, in this graph, let's take a look. This is piecewise cubic cubic polynomial. This is not continuous, all right? But when you impose continuity constraint, they are joint. But in this graph, is the green graph smooth, Hirawat?
No.
No, not smooth yet, because it seems that, because if you take a look, it's kind of a little kink, right? A little kink here, which means that at point C, the derivative, all right, limit from the left, limit on the right, they are not equal yet. They are not the same. That's why when you impose smoothness constraint, the graph will be smoother. But one note in here, whenever you, for example, if I want to illustrate, suppose I have P1, right? My P1 is second degree polynomial, and my second polynomial is okay. My second polynomial is given by gamma. Okay. Sukit, can you take derivative P1x? P1 is?
P1 is
Prime.
P1 prime is beta 1 plus 2 beta 2x.
Now, what about P2 prime? What is it?
Gamma 1 plus 2 gamma x. Oh, gamma
Plus?
1 plus 2 gamma 2x.
Okay, now I'm going to evaluate at some point, right? So it's going to be beta 1 plus 2 beta 2 C plus gamma equals gamma 1 plus 2 gamma 2 C. Remember the breakpoint is given. The breakpoint or the knot that you want the smoothness constraint to be satisfied. And now in terms of model estimation, whenever you impose one constraint, you see in this example, now beta 1 and beta 2, gamma 1 and gamma 2 are no longer can no longer be chosen arbitrarily because they have to be coupled by these yellow constraints. So these mean whenever you have one constraint, it just free up 1 degree of freedom. Your degree of freedom will be reduced by 1 if you have one constraint. Okay. So now, so the spline is the piecewise polynomial where you impose constraints on the continuity and the smoothness of your function. So we say a degree D spline, all right, is a piecewise polynomial of degree D with the continuity constraint in F, all right, in F prime, blah, 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 up to the degree D minus 1 at each knot. Okay? Okay, now let's see some example. This is, suppose you have splines, all right? And of course, in order to estimate the model parameter, now we're gonna represent all the spline in terms of basis representation. Here I give you just some example of common ones. Okay, linear spline, cubic spline. Suppose you have k knots. Okay, k knot, and in this example, I'm gonna let k be 2. Only 2 knots as C1 and C2. Okay, so as we see before, if we have k knot, right? C1, C2, and CK. So you're gonna partition the regions of X into k plus 1 region. So you have k plus 1 region, okay? And then per region, in one region, it depends on the degree of polynomial you use, right? So at this step, I'm going to count how many parameters does it require? Is it required in spline, all right? So it depends on the degree of polynomial. Let's say this is the number of parameters per region, and then you multiply with k plus 1. But then those piecewise polynomial has to satisfy constraints, all right? So on the left-hand side, if I try to count how many parameters of splines, I would count total number of degree of freedom, subtract by the degree of freedom that I lose from obeying the constraints, all right? So if you have k knots, right? So you have k constraints. Sorry, if you have k knots, so this is going to be k, all right? And each knot, how many constraints? It depends on how many constraints per knot. Everyone follow here? Right? So right? This is very straightforward. How many knots you have and how many constraints per knot you have. All right, with this multiplication, that is the degree of freedom you lose. All right, and that's on the left hand side is a total parameter counts. Let's see some example. Now, for linear spline means that you use first order polynomial in each interval, right? Number of total parameter counts in the linear spline would be of course k plus 1, right? And for linear spline, how many parameter per region? It's going to be 2, right? So it's 2. And here is the number of knot k. And if you use linear spline, if you use linear polynomial, per knot, in one knot, how many constraints do you have? If you use first order polynomial, right, you only need to satisfy continuity constraint. So that one constraint. Okay, so this number and this number, it turns out to be k plus 2. For linear spline, the degree of freedom, linear spline with k knots, okay, would have total parameter count of k plus 2. And this is a way to represent the basis function that represent linear splines, all right? G1, so now I illustrate with k equals 2, all right? They have not as C1 and C2. So for linear splines, you know that everything will be, of course, I mean, the basis function will be, I mean, can be up to first order, right? So you have 1 and x, okay? For G3 and G4, we use the, so this notation, it means that this is linear function in x, right? Suppose C1 is here, but you just take the positive part. You take the positive part, so its graph looks like this, the blue color. Okay, and then for G4, the breakpoint is here as C2, so the function G4 will look like 0 all the way here, and then is linear. Okay, it can be shown. This is a good exercise that G1, G2, G3, and G4, these are basis functions of linear spline with what? With 2 knots. Okay, when k is 2, you just put it back. K plus 2 is 4, right? When k is 2, so you need 4 basis representations because they are total parameter counts of 4. Next, for cubic spline, so the cubic spline means that the polynomial is third order. Okay. With the same number of knot is k plus 1. Number of parameter per regions. For cubic, there are 4, right? There are 4 parameters. Okay. And then subtract by like the total number of constraints. You have k knots. And number of constraints per knot, what is it? If you have cubic polynomial, so it's third degree, right? So you have 3 constraints per knot. The first one is continuity in P. The second one is continuity in P prime. The third one is continuity in P double prime. Okay, so that's why here is 3 constraints. I mean, you work this out, it turns out to be k plus 4. So the cubic spline with k knots will have total degree of freedom of k plus 4. And yet, this is an example of basis representation for cubic spline. You will have this term, okay, that is polynomial in x0, x squared, and x cubed. And then the 2 additional terms, these are again positive part of cubic function of x minus c1. Okay. Again, this is an exercise to let's confirm. When k equals 2, you need, right? You need what? You need 6 basis representations, and these can be one choice of them. Okay. Now you can see that, okay, when, of course, okay, when we get these bases, what's the step? Of course, if I get to fit the cubic spline, if C1 ck are given, of course, I develop y equals what, beta 0 right? G1 plus, let me use B1, like B2, G2x, right? And B3, G3x, and so on, beta 6 and G6x, right? I just plug in this basis function of my cubic spline. Okay, and then what I do is I just solve for beta k, all right, using the linear regression. And that's when that's when C and CK are given. Okay, are given. But the question is more about how can you design those breakpoints, right? How many number of breakpoints and where they are. So of course, the guideline, the general guideline would be that if you introduce more knots, right? If you introduce more knots, so you allow F you allow the representation, this F, to be decomposed by so many terms, right? If you have more knots. So by doing that, does it increase flexibility of the model or does it decrease, Napat?
More not, right?
More knots.
The flexibility increase.
Yes. So the general guideline, if the more knots you add, right, the more flexible model you get, of course. And where you should place the knots, of course, it depends on the behavior of the data. So suppose if I right, maybe not clear. Suppose my data look like this, of course, right? So of course, I mean, it's not necessary to put knots where my response seems to be like steady. You only need to make a knot where you see some trend, some change in the response, right? And that's the general guideline of how you place the knots. But of course, in practice, like you may want to come up with some algorithm to choose this for you. So in this example, we the same data set, the weight data set, right? And when we specify that we want the spline that has total degree of freedom to be 4, okay. Okay, and in this example, the knot locations are chosen automatically by sorting the data and look for the percentiles of the predictor. Okay, and of course the number of knots can be chosen from the cross validation as well. I would like to make a note that there are many rules. All right. Okay. This approach that is actually is taken from the book, the ISR book. I believe that there's a way that they handle this in R in the program as well, where you can select you can select this location according to this rule. Okay, the number of knots that I say can be chosen by using the cross-validation approach. Is this the same thing as we discussed before, where you all know that the model selection, which means that you try to pick the model flexibility at the right amount, right, by using the cross-validation. So it means that you're gonna partition by cross-validation. It means that either you do the validation set, either you do the leave one out, all right, or the k-fold. So what you're going to do is you're going to perform an experiment where you increase, where you vary the number of parameters, vary the degree of model flexibilities. In this context, you can vary the number of knot, right? And then you observe the the model quality in terms of you can test it with MSE, right? So this is CV cross validation error. Okay. Suppose and of course you know that number of knots, right? Suppose you evaluate this MSE in the training data set. Training, you know that the trend would be, what is it? MSE, how can you?
Monotonically decreasing.
Because more knots, more flexible, right? But that, again, but if you test it on the validation data set, that's no longer true. That's why you want to observe how it turns out. So if the test MSE look like this, right? All right, it means that, okay, probably around here, that could be an appropriate degree of appropriate level of the number of knots. Okay. Here I try with some commands in MATLAB, all right? I feed a cubic spline using this command, okay? This is solved by linear least square approximation. On the top row, so this is a cubic polynomial fit without constraint, like continuity in the polynomial, in the derivatives, all right? In the bottom row, all right, we consider two cases, 3 knots and 5 knots, all right? With this command, I specify the number of knots I want, but the locations are chosen by MATLAB. And then there are many ways, as I suggested before. This is the one. So there's some rules, some condition where of the locations of knot to be satisfied. So it has to lie. It has to lie, you know, in the X, and there's more information you can read further. This is acceptable knot. This is optimal knot, augmented knot, or the new knot. All right, there are many more. 3 knots are blue lined. All right, so the corresponding blue are the locations of the knot, right? And 5 knots are the red ones. So in terms of these, you see that visually that when you use more number of knots, the curve, the red curve, can represent a more rapid change in the function. Okay. Okay. Here's the next one. All right. When we have spline, of course, as I said before, when you train the model, sometimes you use the model to explain the data, the unseen data. And that unseen data can be out of range of X where you use for the train. Okay. So in this graph, if you just implement spline, if you take a look at the blue line, right? The blue line. See the end of the end of the curve is kind of increasing here, right? So which means if I use this train model, the cubic spline, the blue one, and I use it for prediction in the new values of X, the new X, right? The new X, where my new X maybe the range is outer range of the one I use for train. Of course, my prediction may have something that unreliable because of these behavior at the tail. Okay, so spline can have high variance. That's the thing. To fix this problem, so there is the concept of a natural spline. Now, a natural spline is actually a regression spline where you add more constraint, and that additional constraint are applied at the boundary, where you enforce, right? At the boundary, you enforce things to be linear. Okay, now I'm going to zoom in. For the natural spline, if you look at the okay, if you look at the red curve, okay, so the tail here is term it has to satisfy the linear, which means the higher order derivative at the endpoint must be 0. Okay, so conceptually, for the cubic spline, right? Cubic spline has up to order 3, right? So we're gonna enforce 2 constraints for the endpoint, for each endpoint. Or that 2 constraints are the constraint on the derivative. So which means for natural cubic spline, all right, for cubic spline, it has k plus 4 degree of freedom, but when you add more constraint on the boundary, so totally it has 4 constraints. Now again, the parameter count is reduced by 4, so totally natural cubic spline has k degree of freedom, k basis functions. Okay. This is a comparison to like between natural cubic spline and when you fit basically a polynomial degree 15. So degree of freedom in the natural cubic spline would mean that it requires 15 basis functions, right? So it is number, but when you fit a polynomial degree 15, you need to the whole, like you use D to represent like the whole range of x. So which means that this is a model where you have like x to the 15 here. Okay. So this is some graph to represent that when you use high order polynomial, right? Sometimes these model will not generalize well because so the curve can change too abruptly at the outer range of x. Okay, while in the natural spline you force the ending, the boundary, to be linear curve. Okay, so it gives you a more reasonable fit. Now we have seen regression splines, natural splines. Next is and the last concept is a concept of smoothing splines. All right. So without a function, now I would like to get right into the definition first and then explain the connections. So suppose we have the problem that we want to find some functions, okay, some functions that has 2 continuous derivatives. Okay, f prime and f double prime, and you want to find the one that minimize these loss function. The loss function, these represent now there's a parameter lambda. Now let's take a look at the first term. So the meaning of the first term is just the conventional sum square of the residual, right? So this is the error EI, take the square and take the sum from all samples. All right. Now it's not clear yet, but I mean the hidden parameter is within the function f. All right. The function f is the one you want to find. Okay. Now the second term. The second term, we have this integral of f double prime magnitude square. So think about this. Suppose this is your t, this is your f, right? Okay, and then okay, your f double prime is also a function of t, right? This is how the function, how the slope change over time, right? F double prime is the f double prime, of course, f double prime is derivative of f prime, but f prime is the slope of f. So f double prime just suggests how the slope is changing. Okay. So of course, if f double prime is huge, your curve is gonna look very high fluctuated. So when you look at the integral of f double prime square, it means that you look at this graph f double prime t, right, and you look and then square it in some sense, and then you look at the integral under f double prime square. So it's like you aggregate, when you look the area under some curve, you aggregate all the energy, right, of this curve. So this integral represent the total change, total, by the fact that you use the integral action, you use the integral operation, the total change in the f prime, and that gives you a degree of smoothness of f. All right. So if the graph is smooth, basically means the graph is smooth, mean that the graph doesn't change too abruptly, right? That means the second derivative is small. So when you consider these loss function that consists of two terms, right? Consists of two terms, and the latter term is actually weighted by lambda. Lambda is called smoothing parameter. So when you pose a problem like this, it means that you want to find f, right? That the first goal is to explain the data very well, measured by the sum square error. But the second term is you want f that has low curvature. Okay. When lambda is 0, when lambda is 0, you have no penalty on these at all. Okay, so that's going to fall back to the problem of fitting graph. Just interpolate the data. Just look at the data points and fit it. But when you increase the data to be large, all right, which means that now I really want my f to be really too smooth, and I care less about how it fits. Okay, so when lambda is really big, f is going to be close to a line fit, right? Because a line fit, it would have 0 second derivative. Okay. Now this is some theoretical results that the solution to the minimization of this guy, all right, it has the property, it has the following, the three following properties. It turns out to be a piecewise cubic polynomial with knots at every unique values of x1 xn. Okay, it has continuous first and the second derivative at each knot, and it is also linear in the region outside the extreme knots. Suppose you're given data x1, x2, and xn, all right? So in the second property, it means that it has continuous first and second derivative at each knot. The third one, it means that it's linear outside the region of the extreme knot. The most important one that I want you to point out is that I mean, this is an exercise, right? I haven't given a proof yet, but it's an exercise in the book, which means that it can be shown that the solution of the loss functions in here is satisfy these three bullet properties. So, but these three bullet property is actually a property of what? Natural cubic spline. So this is an amazing result, right? That in fact, the natural cubic spline, when it defined at the knots, where are they? The knots are actually all the unique points given for the analysis. Okay, so that's the important result. Okay, but one thing to point out is that this is the natural cubic spline with the knot as x1 and xn, right? So we claim that it's a solution of this problem, but this is not the same as the natural cubic spline. We would solve it from the basis function approach, which means if I solve, so if I say, okay, I'm gonna come up with a natural cubic spline, I define the knot at x1 and xn, and I solve it with this way that I explained before, that that my fx is going to be beta 1 g1 dot 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 beta beta n gn, all right? And I solve it for beta k. So this is the basis function approach. When I solve it, these coefficient beta k will not be the same one as I solve from this functional optimization. This one will be a shrunken version. And what we mean by shrunken, I will explain a little bit shortly. Not sure if you follow this. Okay, but now let's see this slide to see how we get the solution. All right. First of all, with these important results, that the solution has this property. The solution of the this loss function optimization is satisfy these three properties. It gives the natural cubic spline, right? So now we assume, okay, of course, now let's assume that, of course, the natural cubic spline defined on the k knots, right? N knot, sorry. So I let it be hj. So my representation would be this, okay? Hj is a basis function for natural cubic spline, which means all the constraints are already taken into account. The constraint on the continuity in the polynomial, in the high order derivatives, and the constraint on the ending points at the boundary. Okay. Now if I construct a matrix H, big N by big N, where my Hij is the basis function value of the jth basis evaluated on the I sample. So visually, so you take a look at what so the first row of H is going to be H1, H2, dot Hn, right? You use the first sample of X evaluated on, all the basis functions. Now, next, the function G, sorry, the matrix G. The matrix G is taken by, the G is a square matrix, all right? Square matrix, where the JK entry is given by what? The product between Hj and Hk basis functions, multiply, and then integrate. I would like to mention that this is actually inner product in the functional space. If you study more about analysis, all right? So this is the continuous function form a vector space, and where we can define inner product of functions. So now I would like you to imagine that, for example, the matrix G is n by n. The diagonal, if you look at the diagonal, okay, Sukit GII would be from the definition. GII would be
integrate of hi dot
double prime
hi double prime is a
square. Yes, okay. If you look at the diagonal, all right, okay, Sukit, this function hi double prime square, is this function non-negative?
Yes, it's non-negative.
I mean, double prime itself can be both like positive and negative, right? Because that's how the slope changes. But if you square it, it's gonna be non-negative, right? And you basically look at the area under curve. So which means G11 here, that's the area, that is the energy of H1 double prime. G22 is the what? Is the total energy of H2 double prime. Diagonal entry are non-negative. That's the first thing. Okay. And of course, by the definition, this is the inner product between second derivative of the jth and the kth. So this metric has a name, all right, but like it looks like a gram matrix, all right, but I'll leave that for your further study. But I just would like to point out one obvious property is that first G is square. Secondly, is it positive, Panat? Sorry, is it symmetric, Panat?
Yes, Ajahn, it is symmetric.
If you look at the blue, all right, this is like coordinate 1n and n1, right? They are the same. So this G is symmetric. Okay. It's also positive definite. But I leave that as further reading for you to prove. All right. Okay. Okay, and then when we formulate in this way, remember that we have the loss function as a sum yi minus fxi square, right? Lambda integral of the f double prime square dt. Okay, now because my f represents as this summation, right? So my f double prime is of course my f double prime t is going to be the sum of ji over n beta j f j double prime t, right? And then maybe an exercise for you, because this is going to take some time. This is going to take some time for you to see that these integral, all right, can be represented in a vector form as B transpose TB. Oh yeah, this is a good exercise homework. Okay, maybe the last one, because today is the last lecture. All right. Okay. By using this basis representation, how about like, remember that this is beta 1 h1 double prime, right? Beta n hn double prime, and then you're gonna like square, right? Make an inner product, but of course trying to use a vector notation so that your analysis is like easy to follow. Because maybe I can introduce like, so this is going to be of course vector beta transpose with h1 double prime. Okay, all right, so your f double prime t is this, right? So it's inner product between two vectors, and then you try to use square and then integral. Okay, please show that it can be written as beta transpose G beta. Okay, and then this first term also. I shouldn't. Okay, and also this first term, this is the residual sum square. It can be represented by this matrix notation. Okay, now the parameter, when you have this basis representation, you see that initially the problem here is an optimization in the functional space where you want to look for f, but now you parameterize f as with the basis representation, right? So now the parameter to be optimized is now becomes a finite dimensional vector beta. So in here, if you want to minimize this, this is to be minimized with respect to beta. Okay. And of course, I'm going to remove everything. Now let's take a look at this. All right. This is some, I put a note that this is some, let's say some function. Let's say I use G, right? Like everything here is a function B, G in beta. Now, if you can recognize, this looks like, this is nothing new. It looks like what we have done before in the weighted least square. In a linear regression, right? This term is a linear regression because this is y minus h beta square. All right. This one is what? Weighted norm of beta. So again, I will ask a very good exercise. Generally, you can say that this G is quadratic, right? Quadratic in beta. And the solution, which is given by taking the gradient, set it to 0. This is what we have seen before in the Reinsch regression. Okay, we can prove that beta hat is given by this. And this inverse operator here is always, I mean, this matrix yellow here is always invertible as long as lambda is positive. Because even though this is positive semi-definite, this is positive semi-definite, oh, but this is positive definite, right? G, positive definite. I mean, I haven't shown, but I state this as a fact. So when lambda is positive, the whole thing is always positive definite, which further means it is invertible. Okay. Now with this expression where to be proved in your homework exercise, now you see the role of lambda here, just like the role of lambda in the Reinsch regression. What happened when lambda is big? True. When lambda is big, what happened to this inverse? Is it small or large?
Yeah, small, Asha.
Small, right? This, I mean, of course, this matrix is big, but with the inverse thing, it becomes small. So what about beta hat, Trung?
Small, Asha.
Will be small. But when this is an overall observation, right? Beta is a vector. It's small in the norm sense. Now, I mean, initially we see the role of lambda here, that if you penalize lambda even more, right, your solution should be what? Your solution f, your function f should be smoother. Now, we will see how to support that as well at the end. But of course, one thing that I would like to make a connection between what we have seen so far is that you see that when you solve the smoothing spline, the solution is given by this. Your beta here is a coefficient of a basis representation of the natural cubic spline, and this is what I mean by the statement that this is not the same as we solve natural cubic spline from the basis function approach, because what you see that from this smoothing spline approach, it has the role of lambda and g, and that is a term you penalize on the second derivative. It is introduced in here. If you solve natural cubic spline conventional approach, it would be just this, right? Just like the least square solution. Okay, so they are not the same. Okay, now let's see furthermore on this representation of the solution. Okay, when we have beta, so this is your beta, right? And your h is this, right? So this is h1, h2 by the column. So it's all the basis function by all rows, right? By all rows, this is the sample index, right? Okay, and then suppose I get beta hat. I get beta hat. I want to do the prediction on y. Okay, what do I do with this beta hat? Tila what? Tila what?
Can you repeat the question? I don't quite get what you asked.
The question is, we already solved, right? Smoothing spline, the solution. The parameter of the smoothing spline is actually this beta hat. But when you want to compute its prediction, its fitted value, which is y hat. So I'm asking how to get y hat. What to do with this beta hat?
You have to.
And it's h.
Y hat equals.
Y hat, it could be this, right?
Yes. Yeah.
So it is. So it's multiplied with beta hat, right? Because because each row of h, it is a value of basis, all the basis function. So you're gonna what? You're gonna make inner product, and that gives you the sum, right? Give you the sum. So for to get f hat, right? This is beta hat. So we multiply beta hat with h. Okay, with h here. And everything here before the matrix, before the vector y, we call it s lambda. It's associated with lambda because lambda is there. We call S lambda as a smoother matrix. Smoother matrix depends on H and lambda, but what about the H? H, remember, H is what how you evaluate the basis function value on each X. So we say principally it depends on X and lambda, the smoother matrix. The smoother matrix is symmetric, right? I hope it's clear. Okay. And it is positive semi-definite. Okay, that I hope that is also clear. Given I say that my G is a positive definite matrix, right? That means the rank of S, the dimension of S is n by n. Okay, we can show that the rank is full rank as well. Is big N, and this one may not clear and obvious, but I stated as a fact as well that if you operate the smoother matrix twice, it's actually less than the original one. So the meaning that is like, oh, this matrix is shrinking. You apply it twice, it's less than in the matrix sense, less than the original one. Okay, which means when we solve the smoothing spline, people define the degree of the smoothness via lambda, right? For each lambda, you get a smoother matrix. Now we know that the solution beta depends on lambda in this way, okay? And we sketched previously that lambda is big, beta hat is small, right? Now, how can we explain when lambda is big, all right, F is right more smooth, right? More smooth. And then by varying by varying lambda, which means when lambda is really big, your F is gonna tend to straight line, right? So it means that as lambda is bigger and bigger, your kind of your model flexibility decreases. Everyone convinced? Is it okay? Everyone is okay with this? It's good
Yes,
so
understand.
far. So when lambda, so we try to come up with a way to explain this. Okay, when lambda is big, we know that model flexibility is kind of decreased, right? Decreased. Okay, but the way we quantify this degree, how? So we use the concept of effective degree of freedoms that can be measured by from smoother matrix. Okay, so the effective degree of freedom of a smoothing spline or DF, and it depends on lambda, is defined as the trace of the smoother matrix. The trace is the sum of diagonal. Okay, agree? Now let's take a look. All right. When what? When when lambda is big, what happened? You know that the matrix S, is it big or small? When lambda is big, so it.
When lambda is big,
Just I mean,
small.
to give a sense, because again, in your matrix S, you have this guy inverse, right? So when lambda is big, your S is small. So of course, when the matrix n is smaller and smaller, the trace would be smaller, right? Smaller. So that's why the degree of freedom here also has the same trend as the model flexibility. Okay. So the reason why we associate S or lambda with the degree of freedom because of this relationship, your y hat is S lambda times y, right? So even though, of course, the smoother matrix S is a square, even though everyone knows that, of course, it has some values on the off diagonal, but the thing is, we can just say like loosely speaking, that, of course, in order to predict the first component of y hat, right? So sy, I mean the one element of sy is gonna be an effect, right? The contribution on the first sample y1, right? So with this interpretation, all right, the trace of the S lambda give the effective degrees. Effective degree is less as the smoothing parameter is larger. Okay. Now the next obvious question is how to select the smoothing parameter. And yet again, we can use, because I mean, you see the concept of model selection, the concept of, you know, how you look at the model, you look at both the aspects of model complexity and the fitting, always come around what kind of, regardless of the model choice. All right. So that's why. And of course, you already know the concept of model selection, how to do it with the model selection score, how to do it with the cross-validation approach. And now, when it comes to the problem of choosing smoothing parameter, we know that this parameter will play a role in model flexibility or model complexity. So that's why one approach is, of course, you can choose the cross-validation. Okay. So here I give an example. If you do the leave one out cross validation, okay, lambda is here. You compute the cross validation error. Okay, so of course this is nothing but residual sum square, right? The meaning of this residual sum square with the note that your f hat with the superscript minus I, it basically the fitted value from using smoothing spline that you train by using lambda. But when you fit it, when you evaluate on all observation except the I sample. So this is the left out sample by this notation. Okay, and again, you look at the curve, all right, and you see if there's an optimal values of lambda that minimize the cross validation error. There is one nice result that you remember that when we perform the leave one out cross validation, how many times do we have to train the model? And what?
N times.
N time, right? The N is the number of samples. We have these helpful, useful formula that says this formulation. So this formula that we see here, that it seems that we have to, of course, we have to fit the model N times. But these cross-validated error can be computed efficiently by this formula. These formula, I mean, they are the same, they are equal, right? But then the one thing I want you to make a note is that in order to evaluate this formula, here is f hat xi. So this is the fitted value of the smoothing spline by using all observations, all the samples. But then there's some terms in this formula that involve the smoother matrix. So in terms of computing, of course, we prefer this formula because in order to evaluate it, of course, we can just use one f hat. The model, we train it on the all observations. You may be wondering why can we use this formula? How do you come up with? I mean, this is some, again, mathematical exercise. All right, so this is exercise in the book. It's good to it's good to I don't know, explore this, but we'll see. I'm not sure if you have enough time for this homework set. All right. I give some examples of the smoothing spline. On the left hand side, it is a simulation data set. All right. I vary lambda from small to big. Of course, when lambda is small, the red one, my graph, my spline is still it's still weakly, right? It's still very highly fluctuated. But when lambda is big, the graph is smoother. Okay. If you use MATLAB, I use the fit command with the remember the fit command in MATLAB is very versatile. It has many options. Fit with straight line, fit with polynomial. So smoothing spline is one of the options. Okay, but check the syntax of the command. Of course, I mean, this is how you put the penalty parameter in the MATLAB. It will be the opposite way of the theoretical expression of our lambda. Okay, in this, on the right hand side, this is the photo, the figure from the book, the ISLR book. So two smoothing spline, and so the blue one is the one that lambda is chosen from the leave one out cross validation. So with that values of lambda, you can compute the effective degree of freedom, just like we see before. That's the trace of S lambda. So compared to the 16 degree of freedoms, I mean, but look at the graph, like visually they are quite the same, right, in terms of the fitting. And of course, if we have to make a decision, we can pick a simpler model, right? So the last one, probably we don't have time, but this is an explanation why the smoothing spline, all right, has the meaning of the shrunken version. The shrunken version, because we can show that the smoother matrix, we can show that this is again a good linear algebra exercise. The smoother matrix, when you apply on y, okay, the row of lambda appears here in the denominator. So this is a linear combination of vector UK, which is eigenvector of some matrix, and the terms on the numerator. This is inner product between your vector, your response vector, with this eigenvector. So with this linear combination, it says how each component is shrunken by this weight. All right, there's a row of lambda here in the denominator, which means when lambda is big, so it's shrunken down the magnitude of the resulting vector. So there's more on this reading. So it's in ESL textbook. All right. So in conclusion, regression spline and smoothing spline, this is one extension of using linear regression model by developing a local model for each interval of x. All right, and you can play with the degree of freedom of the local polynomial, where now in the splines, we impose the continuity constraint on the polynomial itself and its high order derivative. Smoothing spline becomes a library command in many languages. So you only need to know the principle that how to choose a smoothing parameter lambda in order to control with the degree of model flexibility.